Okay, here's the next question. This is question 8 of the entire paper. It's the third out of 5 mechanics questions. This is some sort of differential equation question by the look of it. So we've got a differential equation here. Let's have a look at some of the details along the way. So we've got a box. We're given the mass, 2 kilos. We also know an initial velocity of 5 meters per second. We're told that there is a resistive force, 0.4 v squared. We've got to somehow come up with that differential equation. All right. The way I'm going to start this, I'm going to write down F equals ma. And I know that A is equivalent to dv dt. So I feel like that's got to come into it somewhere. So the forces acting on the box, we've got the resistive force of minus, well, I guess it is a minus 0.4 v squared is 2. There we go. The acceleration can be expressed as dv dt. Seeing as the question has that in the answer, I'm going to just chuck that in. And I can definitely see this a little bit. I'm going to maybe take it all over to one side so that it's all positive. So this looks a little bit better already. The only thing different now is the constants. I'm supposed to get 5 and a 1, I guess. I've got 2 and 0.4. They are in the same ratio though, so this is good. If I multiply through, what do I need to multiply through by? I need to get 5, I've got 2. I need to multiply by 5 over 2, or 2.5. If I do that, I'm going to get 5 here and a 1 here. Cool. And I've got the expression that I want to, and I'm going to draw a little box to celebrate. Let's have a look at part B. I have to find an expression for the velocity in terms of t. Okay, so this expression does have velocity in it. It also has dv dt. I feel like this is probably going to involve some integration or something like that. I'm going to need to try and split up the variables a little bit first though. Let's see, how am I going to do that? If I take the v squared over the other side first. Oops, that's not how we do it. Okay, yeah, taking the v squared over wasn't necessary, but I can kind of see where we're going with it now. So I'm going to take the dt up to the other side, and I'll take the v squared down. What will I do with the minus? I guess I'll take that with me. So I'll take the dt up. There we go. So it's not super obvious. I did have to sort of move it over. I could have probably done that better. Let's chuck some integration signs in front of these. And let's attempt to integrate. So we've got the integration of dt there. And let's take the minus out. 5 over v squared here. I can write that a little bit better. I can write that as 5v to the minus 2. Okay, let's integrate that. So integrating dt, I'm just going to get t plus the constant. I'll write it on this side. And if I'm integrating this, I'm going to add 1 to the power and divide by the new power. So adding 1 to minus 2, it's going to take me up to minus 1. And then I'm dividing by that, which just means the minuses are going to cancel out actually, which is kind of neat. So I'm going to get 5v to the minus 1. Apologies about the T, looked a bit funky. There we go. Let's rub that out. All right, what's next? So I've nearly got a velocity expression. Let's just write this a little bit neater. I should probably work out the value of c. I was told that the initial velocity was 5 meters per second. So that means I can plug in v is 5, t is 0. So let's take that expression. Let's do that. So t is 0. V is 5. I'm going to get just c over here. Oh, and I'm going to get 1 here. Great. Let's write the expression again. T plus 1 is equal to 5 over v. And I guess I just need to swap this over a little bit. It wants me to come up with an expression in terms of v. So I need to rearrange this so that it's v equals something. Something I can do, which is kind of convenient, is I can just take the t plus 1 term down, and I can take the v up. I'm effectively swapping these over. Multiply the v up to this side, divide by t plus 1, and there's my velocity expression. Very pleased in a cloud. Kind of. There we go. Nice. So that's part B sorted. Part C. Explain why the model's not particularly realistic. Okay, so this velocity, it's a little bit hard to okay, so we've got a 1 marker left. Part C. Briefly explain why the model is not realistic. There's a nice circle in it. So we need to sort of infer something from this 5 over t plus 1. Now, it's not sort of super obvious, but what you might spot with this is even if you plug in a large value of t here, you're still going to get some velocity. So even if you had like 100 seconds or something like that, you'd still get that 5 over 101. So the object is still moving 100 seconds in, even though there is a resistive force acting on it. So that's the sort of the alarm bell, I suppose. You're not going to get a velocity of 0 ever with this expression. So I guess the justification is the object can't stop in this model. That's a shame, but it gets us the mark.